Thank you, everybody, very much. So my name is Chris Marcellus. I'm here to talk about the digitizing of tailings facility storage monitoring. So I was invited here by our Sequent team. So my goal today is going to be to tell a story of a pilot project that we did with OceanaGold with Sequent and Bentley, and also talk about iTwin IoT, our new monitoring platform, and how it can work within the tailings monitoring industry. So first slide is going to be my introduction slide. This is kind of my highlight slide to make me memorable. So I've been working with Bentley for about 3.5 years now. Previous to Bentley, I was with the monitoring group in the IoT realm, SenseMetrics, if anybody's familiar with them. And I transitioned to Bentley as part of that acquisition. So I've been a solution architect with Bentley for the past 3 years. Prior to that, I was an installation technician for a company called BDI. I'm here, as you can tell by my very American accent, from Denver, Colorado. I've been here since Tuesday. Flown in to present at this event. So I'm grateful to be here and for the opportunity to speak to everybody. But I've been in the IoT monitoring industry, designing telemetry systems, doing rope access, and really a boots on the ground experience that's transitioned more into the software side of the equation since the Bentley acquisition. But with the benefit of having that hardware background and being able to consult our users in the industry. And then previous to that, how I wound up in this crazy world that I'm in, I worked at Cirque du Soleil for 7 years. So I was an entertainment rigger at Cirque du Soleil and learned rope access, learned the ropes, no pun intended, and transitioned from a rope access technician at Cirque du Soleil to a rope access technician traveling the country and the world installing these sensor types. So hopefully that makes me somewhat memorable going forward as we leave here today. So a few things I want to talk about. First is going to be iTwin IoT and the mining industry. So Bentley's iTwin IoT can be utilized to combine traditional IoT monitoring with the technology of a digital twin. So you can see some different screenshots that we have here, one of a reality mesh of a drone flight, one of a geological model that we were able to bring in over an IFC connection, and also some borehole data that we were able to bring in from Sequent's Leapfrog. So really combining the IoT monitoring platform that you're used to and how you can visualize it on top of a 3D realm, combine those things, and then use things such as advanced visualizations like heat mapping, see how your structure is changing over time. If you have multiple digital twin, like maybe you're flying with the drone weekly or monthly, you can bring all those in, you can see how things are evolving over time, and use that in combination with your monitoring data. I got 2 presentations open here. Let's see. There we go. So tailings management solution. So that's going to be the crest of the pilot project that I want to speak about. So Sequent and Bentley's leading practice tailings management solution has at its core a multi-stakeholder knowledge base that enables a monitored digital twin and geotechnical analysis workflow and turns that static data into actionable intelligent live project data. You can be notified of alerted areas in real time based off of thresholds that you've set. And then in an industry striving for best practice in that tailing storage facility management, OceanaGold had a digital response to their Wahi operations, offering a gold mine of information. So with Bentley and Sequent's innovative software, the team created a data-driven digital twin to better understand the physical asset and help manage the safety on site. They were able to eliminate communication silos. They were able to have one source of digital truth with their monitoring data combined with their geotechnical data, their modeling, and combine everything under one roof to ensure that everybody was looking at the same data at the same time, instead of maybe a manual data collection was made and didn't get brought in for everybody to view. They were able to really eliminate those communication silos. And going digital has helped OceanaGold minimize field time, simplify complexities, identify changes, manage risks, make decisions, and collaborate with the engineer of record and the other stakeholders to improve day-to-day operations and workflows and efficiencies. So the agenda, as I get to 5 minutes into the presentation, is going to be to talk about the objective of that pilot project, the why and what they were trying to accomplish, the project's approach and the workflow, and then I do want to get into iTwin IoT and the real-time monitoring solution that we're working on within Bentley and apply to tailings dams today. So the pilot project objective, enabling an easy-to-use, robust solution that can help a TSF owner better manage their tailings facilities and align with the new industry standards. So being able to be up to par with the industry standards as they evolve. The why, structural integrity of tailings storage facilities are critical to community, safety, and environmental protection. So zero harm to humans is a very important thing, obviously. And the challenge was how to go from a reactive workflow to a proactive workflow. Use that plethora of data to be able to visualize it and one single source of truth, as I've mentioned, and have access to that reliable information when it's needed at the tip of your fingers, instead of having to rely on outdated workflows, inefficient workflows, and things that really can bog down a workflow. So the project approach, we instrumented 3 different control sections. We have some world sensing individuals here. We used 3 threads. The thread was a SenseMetrics hardware data logger that is now a world sensing hardware device, but it was used as a gateway in the network. And then we used 14 strands vibrating wires to tap into 38 piezometers to get pressure data, elevation to water, depth to water, and have live IoT data streaming in, as well as a digital twin from Leapfrog and some geotechnical analysis from GeoStudio. We were able to utilize the mobile app and bring in that data in real time, confirm in the field that a sensor was coming in as expected. So parts of the workflow that weren't included, there were a few control sections that weren't instrumented, but there are plans to instrument it in the future. And we didn't include as part of the pilot INSAR, drone data, earthquake data, or geophysics. I'm going to go ahead and tap through here and watch these videos all play. So we do have some IoT monitoring data from SenseMetrics, as well as some Leapfrog modeling and some geotechnical analysis. So any questions on the modeling and the geotechnical, we do have some CEQA guys here that can definitely help you more than I can. But from the IoT monitoring as well, you can see the SenseMetrics workflow going of sensor data coming in, alerted thresholds being triggered, and then being able to action from there. Also using the software as a data repository to bring in IoT data and maybe non-IoT project data. We can also do things like automated reporting on any schedule you want, using that project data to get into inboxes of stakeholders in real time as needed. So that's what I wanted to talk to about the pilot project. It was a successful pilot project, and I would say that there is stuff on the roadmap from that pilot to automate that workflow even more that I look forward to seeing evolve in the future. But the next few slides, I want to go over the iTwin IoT real-time monitoring and what our capabilities currently are in that realm. So IoT asset condition monitoring, you always want to start with the sensor data acquisition. How do we get your sensor data in? Within Bentley, we are strictly on the software side, so we have to tap into different hardware manufacturers and their sensors, but we do have an IoT sensor agnostic approach. We want to be able to get all your data from your different hardware into one roof, so you're not relying on dozens of different logins for dozens of different sensors. We want to be able to be that one source of all your IoT monitoring data. Once we've tapped into that sensor data acquisition, we can visualize and analyze using different modules within the platform. So we have dashboarding ability, data graphing, we can do anemometers and windrows plots, XY plotting with your inclinometers and your slope stability. And then once we have all that information in, we work on the collaborating and the reporting and the alarming and the things that make sure you're notified as soon as you need to be notified, as soon as any thresholds that you've set have been breached. So here's that vendor agnostic approach as I spoke to. That big old blue logo is our iTwin IoT logo, and here's just an example of some of the different partners that we have in the hardware network, some of them in this room today. So we're able to tap in, depending on the connection and how we were able to work most efficiently with those manufacturers over either API, MQTT, some FTP pushes, different ways to get your sensor data in from those hardwares. We do have a partner device registry, a repository that explains the different directly compatible sensors that we have. Also, when this presentation is shared out, I did get fancy, and that is a link in the top left-hand corner. It's not just a blue underlined font. So if you are curious and want to use this platform, you can utilize that partner device registry to see what sensors have that direct integration. With all that being said, we also do have a file import tool, an ASCII import tool that allows you to bring in data either over a manual data push or an automated data push over an FTP synchronizer, where even if you don't have that directly supported hardware, you're still able to bring in your sensor data. You can rely on the hundreds of sensor data sources in our library, or if you have a unique sensor type, you can hand type in the metric and the unit of the sensor that you're bringing in and visualize the data that way. As we all know, the IoT sensor market is ever expanding. There are new IoT sensors and new IoT manufacturers every day, and it's impossible to directly integrate with all of them. So we do have the ability to bring in data from different sources over that ASCII import. Here's just an example of our connectivity module. This is going to be that repository of the sensor data that comes in. You have your observation counts, your last observation that you came in. You can visualize alerted sensors directly on this platform. Every sensor will have a configuration page where you can add notes, you can add calibration factors, installation photos, and latitude and longitude location to be able to visualize where the sensor is in real time within the different modules that we have. Our dashboard module allows you to bring in your project data, your IoT sensor data, as well as visual data such as photos and alert summaries, different things like that into the platform. And if I'll go to the next slide, we do have a screenshot here, a screen flow that I was able to bring in. We have an example of a dashboard within our tailings dam module. We can see our pressure data, a polar plot with some anemometer speeds and a needle gauge where we're able to visualize sensors in that regard. And then if I click the plus card here and go through the card types, we see the different 30 types of cards within our library that you're able to have, from diagnostic sensors to graphs to summary cards, things like that. And then we have our sharing settings, the ability to collaborate amongst your project. So within every project, you can have customized roles to pick and choose who is able to do what. And then you can set any profile, be it a dashboard, an alert, a report, whatever it may be, is either private, restricted, or project-wide, to make sure that shareholders are getting informed in time as needed. And maybe, especially with things like an alert threshold, maybe you want to make sure you're going to verify it before somebody else who might not be as involved in the project gets alerted and kind of rings a panic alarm. So we have different abilities to be able to customize individual profiles to that extent. With alert module, our alert module, we do have 3 different alert types that we support. We have our data alert, which will be your standard thresholds. Apply a threshold and get notified if it goes above or below the threshold. We also have status alerts available to be notified over an outage, and correlation alerting, where you can choose 2 different sensors on your project and apply either a quadratic or a linear formula to those sensors and get an alert off of that bell curve that's exposed by that formula. We also have correlation dashboard cards available as well, where you can choose 2 sensors and see how they're correlating with one another over time. So this is going to be an example of an alert that's currently in a triggered state. If I roll through, you can see a trigger history, what value triggered the alert and when it happened. You can also see a data graph display in comparison to when the sensor values in comparison to the alert threshold that you've set. And then we do have different priorities that you can set between low and critical, and the color scheme that will change depending on the criticality that you set. And then we do have the ability to do alert trigger actions, utilize that IoT functionality. Maybe you have a solar system set up and you have a sensor that's in low power because you just doesn't have the demand to be on all the time. You can change that sensor connection power mode automatically in response to an alert trigger. We can also change the sensor sampling rate to get more data coming in. We can take a photo in response to an alert trigger, toggle a relay device such as ring a siren on site, and we can also generate a report automatically in response to an alert triggering. We also have our issue resolution module. So you can create an issue in response to an alert triggering, and what the issue resolution module does is it just allows you to take it a step further. Your alert triggers, and you can create a work order in response to it. It will automatically populate the sensor data, the lengths of the sensor data, the values and the dates that trigger the sensor data, and you can assign a task to anybody on site in response to that alert triggering, and it will be kept on the platform. It can be exported to CSV so you can stay organized, and we can keep everything on our platform to keep you able to do everything under one roof as much as we can. Automated reporting just utilizes all your different sensor data that you're able to build out and apply it to an automated report that can show up in your inbox at a set time, either daily, weekly, monthly, down to the minute of the day. This can be set up. You can bring in photos, an empty notepad, sections, and as we hover through sections, you can see that there's a hyperlink that's exposed. If you were to see any anomalies within any of those data graphs, you could click directly on it and go straight into the data graph, straight into the module, and get a closer look at what might be going on. We can also add tabular data to this view, alert summaries, use this to really keep track and keep everybody informed on site to what's happening. And then last but not least, we do have our digital twin workflow. So the digital twin module allows you to overview that sensor data. And if I click onto the next slide, I do go through about a minute and a half here where that red icon is going to be an example of a sensor that's in a triggered state. As I mentioned, each sensor is going to have that latitude and longitude and elevation you can set. But if you don't have that surveyed ability, you can actually just snap the sensor into place directly within the module. So any sensor with a hyperlink has a location already, but you'll see with this piezometer we're able to just snap it directly where it exists, and now it's available to visualize within the module. We can also do heat mapping by metric or by alert threshold. The heat mapping by metric allows you to choose any sensor on your project, any metric, and see how that heat map is displayed over time. We can also move the time slider, and as you scroll through the time slider, the heat map will actually change depending on the sensor data coming in on that date. So you can see how the structure is being impacted by things such as climate change, or maybe there was a big storm on a certain day that you're aware of, and you can visualize that way. And then we can also bring in the geological modeling over an IFC, view it in combination with that reality flight with the drone, with the sensor data, and we can also visualize the boreholes. And one of the advantages of the BIM modeling and the boreholes is they come in as individual pieces. You can toggle off and on every borehole. You can build different views as needed to really keep organized, make sure that you're able to visualize the correct spots within the tailings to monitor over time. So that's going to be the end of my rambling at you. I very much appreciate being here and the opportunity to present. And thank you very much for your time. I look forward to connecting after. If anybody has any questions for me, please let me know.
Thank you. So many of you will have noticed that either I'm much younger than my photo. In fact, I'm not Eric so Eric is unable to attend, no problem. So I'll be filling his shoes for this presentation. Okay. So, my name's Chris Fagan. I'm the Deputy General Manager of 6 Sense Oceania, and I'll be talking about comprehensive and integrated TSF monitoring systems. I think you're going to see many of the same themes repeated throughout some of these presentations, but maybe with a few subtle differences.
Up and down keys?
Up and down. Okay, some of you in the room may know about 6 Sense. For those of you who don't know us, I'll give a brief introduction. I'll then talk a bit about our instrumentation and monitoring solutions. We'll then look at a few different use cases, and then at the end I'll make some conclusions and recommendations. Okay, so about 6 Sense Group. So, okay, the presentation on this screen is not changing, but this one is. So, okay. So 6 Sense is offering services across 4 main business areas, from the left to right. So instrumentation and monitoring, this is the bulk of what we're doing here in Australia. Digitisation and inspections, some geophysics and specialised engineering, and then also digital solutions and software. The common theme among these services is quality data. So our job is really to provide data that's quality controlled and it's actionable for our clients, whether they're constructors, mine operators, TSF operators, designers, builders, and so forth. So globally, we've got about 20 different offices with headquarters in France, and locally that looks like this. So our headquarters are in Melbourne. We've got our offices in Sydney, Adelaide, Brisbane with an asterisk because we're setting the Brisbane office up at the moment, and across the ditch in Auckland. When I talk about instrumentation and monitoring, our services locally are monitoring design, sensor procurement, installation and commissioning, automatic and manual monitoring, data management, quality control, making sure the data we're providing to our clients needs to be quality controlled, reporting, consulting, maintenance and troubleshooting. So it's really an A to Z services in terms of instrumentation. Let's look now at some solutions for instrumentation and monitoring at TSFs. And firstly, why do we use a monitoring system? Well, firstly, it's to manage the residual risk associated with uncertainty in design and modelling. So this was alluded to before. When we design tailings dams or structures, we don't know everything, we make assumptions. We need to monitor to understand those uncertainties and also the residual risk in our structures. It's also for early detection of a developing instability. Visual inspections, of course, are good. If we've got sensors deep in the ground, we can be alerted to things that are happening earlier. Could be just for a communication of an alarm exceedance. So, okay, we've got a developing situation, an alarm has been raised. Do we have a structured process through the TARP or whatnot to efficiently get that message out to all of the stakeholders? It can also be used to confirm the geotechnical characteristics are within the expected ranges, and it can ease communication between different stakeholders and help support the decisions that they make. So at the end of the day, what we're looking to do here is develop a common and efficient situational awareness. All stakeholders should understand what's happening on their site, and it should be done efficiently. Looking briefly at the situational awareness maturity model, which goes from low up to common and efficient. So low, this is a site where the data is inconsistent, we don't have all the data that we need, and the parties, the different stakeholders aren't communicating. So this is a worst case scenario. Moving up to diverse, where we may have the data, but it's stored in different places, it's siloed, and different individuals have control of those different data types. Up to costly, okay, this is maybe where we're gathering all that data in one place, but our processes aren't optimised, and it's not efficient. And the top of the chain here, we've got the common and efficient, so all parties have a common understanding of the status on site in terms of monitoring, and resources and time are spent on solving issues, making decisions, not gathering the data. This is really the objective here. I'd say most sites are probably at diverse or costly. A few might be at common or efficient. Okay, so how do we get there? Well, a good start, as was mentioned earlier, is to have an integrated monitoring solution where you're bringing all of that data into a single place. So whether that's your geotechnical sensors in ground, like inclinometers, extensometers, piezometers, above ground or deformation sensors, things like automated total stations or INSAR data, laser scanning, and environmental sensors, dust, noise, vibration, and so forth. Integrating all of that data into a single place, a single point of truth, is very important. Another important thing is to have real-time data collection, which can improve efficiency. Not so many years ago, this would have been quite costly, but now, in fact, it's probably costly not to do this. A lot of the sites are remote, it takes time to go around and collect sensors. It's really a no-brainer to implement an automated real-time data logging solution at your site. There's also, of course, it's not real-time, but it's remote. We've also got satellite-based technologies such as INSAR, and then we've got GPS and so forth. Quick introduction to INSAR. I'm sure most of you are familiar with the process, but basically satellites orbiting at about 800 kilometres above the Earth's surface from north to south They're constantly scanning the ground surface, and between subsequent visits, you measure the phase shift and then derive the displacement. Typical medium resolution satellites shown at the top there, and we can see the displacement along that dam crest. What's that? About 60 mils in three years. So every time the satellite passes, you get a new point on your time series curve. Now, INSAR is mostly used in single orbit, which is line of sight displacement, but if you're interested to use INSAR for horizontal displacement and true vertical, then you need to use dual orbits. So one satellite looks this way, the other satellite looks this way, and then you can decompose the vertical and horizontal movement. So an example of this here you see on a dam, whereby up-down, of course we're getting settlement, but also east-west, it's moving out, so it's sliding down. The important thing to note with INSAR, because of the orbit of the satellites, is that we can only measure east-west horizontal movement. We can't measure north-south. So the orientation of your structure is important before you decide whether to use INSAR in dual orbit. A software, of course, is important. I think we'll see a few softwares today. Ours is called Beyond Monitoring, and a few key features of this for raising that common efficient situational awareness, the data integration, so making sure you've got a platform that can integrate any type of sensor data. It should also be able to correlate data, do calculations and give you data insights. GIS platforms, or GIS-based platforms, are a good start, where you can turn layers on and off and you can comprehend a wide range of sensors and a lot of data easily. Alarm management, of course, was talked about earlier, that's key. Also integrated reporting and journals, so you can make comments on your sensors and explain what's happening. Visual inspection management is also a nice bonus to have. Of course, we know that visual inspections are an important part of monitoring. And also having a software provider that is certified for data security is also becoming increasingly important. So make sure your vendor has the appropriate certifications in terms of data security. We'll now look at a few use cases. I'll look at a small site, a large site, a complex site. I'll touch briefly on a multi-site. So this is a small TSF site, but it's state-of-the-art. You can see up on the left we've got 7 piezometers that are connected to wireless data loggers, and we have a solar-powered gateway. So the whole system is operating, providing data continuously every hour, remotely. No one needs to go and visit the site. We've got reports that are generated every week, and data is being checked against its alarm thresholds. A few years ago, maybe 5, 6 years ago, a system like this might have been quite costly, but you'd be surprised at how cheaply a system like this can be deployed. It really is a no-brainer. Oops. Moving up to a large site. This site has about 2,500 sensors. It's 2 large TSFs adjacent to some open pit mines. There's 11 robotic total stations with about 1,300 monitoring prisms and 1,100 piezometers, some water levels, weather stations, and so forth. Having a system that is capable to integrate this volume of sensors and data is also important. Continuing to look at that site, we can see the inclinometers on the left-hand side displayed in profile view. We've also got the geology mapped on the side to aid interpretation. Up top, we're looking at one of the TSFs, the embankments. The little dots are monitoring prisms, where you see an arrow which is indicating in which direction they're moving, and the length is the magnitude of that movement. And underlying that, we've got isolines, or a heat map, which can quickly draw your eyes to the area that might be moving. And then also INSAR, so a system that's capable of bringing in that INSAR data and processing that is also important. You can see by drawing a cross-section through the crest here, it's really moving. And this site's a more complex site. Okay, it's less sensors, it's about 400 sensors, but there's a lot of different types of sensors on this site. The reason being that this tailings dam is also being remediated and upgraded, so there's additional types of sensors that are required here. So there's a large network of piezometers that are installed, all with real-time data collection that we can follow by the hour. There's also automated total stations, which we can control directly from the software. Okay, so there's no need to use Trimble or Leica software if you don't want it. So we can drive those total stations directly from our software. There's also other things. Of course, we're looking at water flow, but we're also looking at noise, vibration, and dust, which are not always critical for TSS. But in this case, there were some communities close by to this site, so we needed to monitor those parameters during the construction. And then, of course, if we're looking at organisations with multiple different sites or mines, having a solution that's capable of integrating different sites into one platform is also a useful feature. A couple of additional features which can be useful at any site would be tours and campaigns, what we call tours and campaigns, and these are used to manage manual sensor data collection. At many sites we have automatic data collection, but there'll always be sensors that need to be collected manually by going and visiting and reading those sensors. Okay, so if we set up a tour, basically we say, okay, sensor A, B, C, D, E need to be collected every second Tuesday. We can then push those out via campaigns to different users, and on the phone they'll receive a map of where they need to go, and then they'll be able to upload their measurements. When they upload their measurements, they'll be able to see a history of the measurements also to make sure that they're not putting in the wrong measurement. Of course, you can then review those on screen. Having a software that also has a toolbox to be able to do manipulations of the data is important. Things like error corrections or offsets or automatic error corrections are important. Also, having those features to be able to track your alarm notifications or journal notes directly on the sensors and interrogate those through the graphs is also important. And also being able to disqualify data. We never delete data, but disqualifying that data is sometimes important. Also, having a mobile application for alarm management can be a good idea. Of course, alarms are normally pushed out to emails and sometimes to text messages, but by using a dedicated mobile app, you can get a lot more information from your alarm. So via a push notification, you can receive the alarm, you can interrogate the sensor data, you can look at how it's performing, you can acknowledge that alarm if you want as well. And then also system alarms, for example, for no data. So if we aren't receiving data from a given sensor, having a no data threshold alarm is important. Visual surveillance inspections are also a great thing to be able to incorporate into your monitoring software. So we have a software called Beyond Patrol, which is used for this, whereby you can create a visual inspection plan with different checkpoints and also what you need to do at each checkpoint, whether that's take photos, make notes, check different things. We can then schedule those visual inspections and push them out to the various users. Of course, benefits of this might be standardizing your process, and also having that inspection data alongside your monitoring data in the same system can be quite powerful. And also having dashboards which can quickly draw your attention to important aspects of your site is also important. So conclusions and recommendations. So these are conclusions to create this common and efficient situational awareness that I mentioned. Firstly is that one size doesn't fit all. So as a TSF operator or engineer, when you're specifying your monitoring, carefully write it, don't copy paste. We see many specifications copied and pasted using old technology, so think about your monitoring specifications and consider the wide range of instrumentation that is available. Consult your vendors and your partners. There's often new solutions and new technologies on the market that can bring much more efficiency to your site. Carefully select the monitoring platform, and you can hear a lot about this today from us different vendors. But of course, it needs to be holistic. We're looking to de-silo that data. We're looking to get all of that data into one platform. Make sure you select the software that is capable to do that. Nowadays, with cloud services, make sure your vendor has the appropriate cybersecurity certifications. And it can also be important for quality and productivity. Now, of course, monitoring software is not going to help you pull out more ore out of the ground, but it can alert you to developing situations, developing instabilities, which you can plan around, which of course can help productivity. Don't underestimate data management. So we will always provide a data manager with a project, and that data manager's role is to ensure that the data on the platform is quality controlled, that the client has data that they can trust. So don't underestimate this. Installing a monitoring system is not set and forget. You need to follow the data and make sure the data is correctly reported. And at the end of the day, what we're looking for is data availability and data quality. These are everything, which means that when you need the data, it's there, it's available, it's on the platform, and that when you look at it, the quality can be relied on. Okay, so availability and quality are key. Thank you very much.
Hello everyone. My name's James. I come from GeoMotion, and I'm here to talk about maybe something a little bit less physical, but more of an idea. Hopefully it doesn't come across as too navel-gazing, but it's the human aspect of a TSF monitoring system. So something that's often overlooked is the actual human input into the system. You know, we've got all these fancy systems, but there is, at the end of the day, a human at the end of it that needs to interpret all the data. So yeah, monitoring systems these days, they're getting very, very powerful, as you've seen two very, very powerful examples already. But they're far from all powerful. You know, at the end of the day, there has to be a human at the end. As technology rapidly advances, more tools are available to us, so also increases the complexity of those tools and the software available to us. And for some people, it takes years to fully familiarize with these different systems. Instruments, sensors, how they interact with the Earth, all while striking a balance with the expectation to mine safer, faster, and more sustainably. Artificial intelligence, machine learning, they're generating a lot of buzz pretty much everywhere, but you know, in our industry as well, you know, it's starting to pop up here and there. But these are all fed off huge sets of data, and will these large data sets collected by the mines and things like that ever be available to train these models? So they could be inaccurate for a very, very long time. So the human aspect, it seems, of a monitoring system will be, for a long time, the most crucial aspect. So the general flow of data on a project pretty much looks like this. You've got a sensor that's sensing some sort of physical change in the Earth. That gets read by a data logger that converts it into ones and zeros, and then radio and whatnot. Goes onto a data management platform, of which you've seen a couple. But at the end of the day, there's analysis and decision making that needs to be made on that data. So for your convenience, I've highlighted in orange every single step of the way that requires some sort of human input. So pretty much everything. So human aspect of sensors. You know, there's quite a lot going on here. These are actually when they actually go in the ground and what they're monitoring. You know, are they being installed to manufacturer instruction? You know, grout properties followed, methodology followed. Are the installation records detailed and accurate? You know, have you verified the installation? Are they installed safely at the end of the day? You know, is there any post-installation support available to you from the manufacturers or from the commissioners? Innovative solutions able to be built to solve issues on site. For example, if you're in the middle of nowhere, can you get satellite coverage if you don't have 4G or 3G? is the Commission focused on data quality? Things like sanity checks are really, really helpful. You know, if you install a piezo 5 meters deep and it's reporting, say, 10 meters equivalent of water pressure, perhaps something is wrong and you might need to replace it or have another look. The human aspect of data loggers. So there's quite a lot going on. Even these days with our, you know, fairly easy to use streamlined systems, you know, they need to be set up correctly and, you know, custom set up for each instrument. You know, is the installation protected? Is it able to withstand site conditions and survive for a long time? Sometimes these are in the ground for 20 years and they need to be able to be built to withstand that. Is there an adequate allowance for maintenance? You know, these days, very, very long battery lives, but it's not infinite. Do you need solar power, or do you just need to have somebody go out there once every 5-10 years to replace batteries? Radio system, you know, even these days, you know, the load sensing system is it's very easy to use. The radio configures itself, but you know, you still need to have some sort of human input there. Sometimes, you know, you might need to fix something or change settings here and there to optimize that system. So, human aspect of data hosting. Yeah, there's a lot going on here, as people have mentioned. You know, there's usually some sort of a cloud service that acts as an intermediary between the data loggers and the data logging system and your monitoring platform at the end. You know, that needs to be high uptime. You know, if it goes down, you lose all readings. So it's pretty crucial. Performance needs to be monitored, so you're not running out of, you know, memory on your servers and whatnot. It needs to be set up properly and particularly these days securely. Last thing you want is somebody else getting access to your data, especially if they're a bad actor. Your MIMS platform, you know, you need to have things like a consistent approach to calibration, which helps when you've got data managers on the project, things like that. And you also need to be ensuring, as Chris mentioned, quality control on the measurements. Actively maintaining the monitoring systems is key. It's key. You know, so data management services really make that process much, much easier. So, arguably the most important is the analysis and decision making based on that data. It's something that we can't directly help you with, but we can assist where we can. But you know, deriving actionable insights from that monitoring data is ultimately the point of why we're doing all this in the first place. You know, you need to apply expertise and critical thinking to the raw data. For example, here, this is a screenshot from a YouTube video where a guy's connected his piezometer to his tap and then turned it on. So he's monitored it for about 24 hours, and you can see there's a clear diurnal cycle there. So it raises up overnight as they're recharging the water systems, and then drops down during the day as people are showering and, you know, cleaning their dishes and whatnot. But even in this example, you know, you'd think it'd be pretty straightforward, but there's even unexpected data where localized spikes here and there, pretty much always, but it actually comes from people within his own house using the water supply, which, you know, creates a higher magnitude difference in pressure. So it just goes to show that, you know, even a fairly simple instrument still requires some sort of analysis. Because, you know, at the end of the day, we need to inform teams for safety, progression of works, design changes, etc., etc. So this is a pretty interesting example, but this is essentially Leonardo da Vinci's first foray into geotechnical monitoring. So his idea was basically dig a shaft underneath this potential landslide surface and then flatten a surface basically a foot wide from bottom to top, and then smoothen it. And then theoretically, if that landslide is moving over time, it will no longer be smooth. So obviously there's quite a bit of human interaction there. Somebody needs to actually go in there, which is not quite so safe, but you know, you ultimately need somebody there to do it. So monitoring systems, they're often launched and then promptly forgotten about until they're needed. But they're still in the background expected to function effectively without any input. You know, near continuous construction on some tailings dams means that the environment's ever changing. You know, instruments get knocked out, destroyed, cables cut, etc. I'm sure everybody's familiar with that. And also, while all that's happening, data is building up over time, generated by sensors, satellites, radars, etc. You know, that data needs to all be cleansed and filtered on a regular basis, so that you're not ending up with, on the previous slide, noisy data all the time, because it's probably not representative of real ground conditions. And as we go on, newer technologies, they're producing more and more data all the time, as you'll see. So fiber optics, they essentially the same cables that feed your internet at home, so you download your dog and your cat videos. Same principle can basically be manipulated for geotechnical monitoring, basically monitoring the change in the cross-section of that fiber optic to get strain and temperature. So the ability to get these distributed, dynamic, accurate, high spatial resolution data is absolutely amazing, wonderful, very, very powerful, but some caution needs to be applied at the end of the day. Systems are already complex. You've got satellites and complex instruments all the time, and there's always complex ground conditions and interactions with different soils. And this system in particular would generate a significant quantity of data, and there also needs to be systems in place there to filter, process, and make that data actually usable at the end of the day. So hardware, software, commissioning, maintenance, technical support, training, data management all need to be considered when implementing a brand new system such as this. However, if these techniques are all mastered, then technology such as this offers fantastic benefits for TSF monitoring. So the champion. they're not exactly Superman, but I'd like to think they're pretty close. So quite often when a monitoring drops in efficacy, it's because it's quite simply forgotten about. People get busy, falls at the bottom of the list. It happens all the time. But in my experience, almost all monitoring projects need a system champion to tie it all together, and TSF monitoring is definitely no exception. There needs to be somebody who's pushing for quality monitoring, whether they're doing it themselves or delegating it to other people. They need to be asking the question of, what problem is this new instrument solving, or what question is this sensor answering for me? Not necessarily just throwing more monitoring at an issue. They need to be enforcing equipment specifications, making sure all instruments are working to specification. They need to be providing solutions to technical difficulties on site, helping out here and there. Enacting quality control and measurements, and actively maintaining the monitoring systems. Quite often that's delegated. And then they're also usually the ones that enact the action plan at the end of the day when something goes wrong. So to tie it all together, they quite often carry the not so easy burden of distilling all this information from all these different sources, applying context to it from ground conditions and site works and whatnot, and then communicating that to a whole bunch of different stakeholders, some of them technical, some of them non-technical. So there is an inherent challenge in communicating this data, usually for the champions. Modern monitoring systems, they produce huge amounts of data. There's a complex interaction with geology, weather, works progress, site works, everything. And you don't really get to have any control on that, unfortunately. So there's labour shortages, and geotechnical engineering means that there's a skill shortage in people who are experienced in looking at this data. And in some cases, this data is very difficult to effectively visualise. The subsurface movements, and some of them would be pretty much imperceptible or invisible to the naked eye, especially when you're dealing with movement over time. So this one over here, there's no more than 30 mil of movement, is that big, but it means big in a geotechnical engineering context, but almost invisible to the naked eye. ISO standards are still being developed. There's only a few instruments covered at the moment, and there's new instruments being built faster than we can build standards to, control them. There's no technical reference really for analysing or interpreting the data from these instruments, or recognising errors when things go wrong. There's no real rock-solid single reference for it, so it's quite difficult to realise, and it's all essentially based on experience. So TSF failures, I'm sure we're all familiar with the photo on the right, and they're unfortunately common, and we are no exception here in Australia. There's a mine TSF failing recently within the last decade, where inside data that they've done post failure showed very, very clear movement in the lead up to the collapse. For 2 months beforehand, the structure was definitely moving. Something on the dam wall was for sure changing, and not in a good way. So fortunately, it wasn't as catastrophic as this failure, for example, but lessons still need to be learnt from it. Could this failure have been prevented or mitigated? Might not have been as bad. if monitoring data was actively being reviewed at this dam. If there was a champion actively reviewing the data with and then correlating it to site activities, I'd say that it probably wouldn't have happened, or it would have been vastly mitigated. So it's seemingly inevitable that more cases such as this will pop up. Tailings dam failure rates are actually increasing over time, and it's only going to get more and more important that we have people looking at it and analysing it. So, ultimate recommendations: how to make it as easy as possible to get it right. Leaning on manufacturers, instrumentation specialists. We look at data all the time. I look at data every day. It's my favourite thing. And we'll be able to pick up issues quite easily. If you're having an issue, then chances are somebody else has had the same thing, and we're able to link it all together for you. Doing things like keeping on top of system maintenance, QA and QC, as Chris mentioned, is absolutely essential. Especially when you're working on multiple projects, sometimes you'll lose that context. If you're actively working on one and then you come back 3 months later and then you've forgotten everything that's happened on it, it's definitely difficult. Data management services, absolutely crucial for that. They make it so much easier for you. And another big thing is implementing your systems in a way to reduce human error as much as possible. So doing things like retrofitting manual monitoring with automatic loggers. We did one recently where a guy was going out every quarter and measuring hundreds of different sensors manually, and then took him 2-3 days, and then another 2-3 days to then write a report on it and then apply calibrations and whatnot. So not only is it huge man hours, boots on the ground, it's a health risk having people on site, it's also a waste of his time really. He could have been doing something different. Environmental effects in different processes make repeatable readings for doing something like a manual data collection really, really difficult. A manual survey might be different at the start of the day versus in the middle of the day due to environmental effects, temperature and stuff affects every single sensor. And an online platform will allow multiple people to review multiple data that multiple projects all at the same time. Makes it much, much easier, especially these days. People are working on 3-4 multiple different projects at a time, and having the same platform control all of it is a big help. User-friendly, intuitive interfaces really make that much, much easier. The last thing you want to do is have to go through a brand new system and learn how that works and then switch to a different system, etc. Just make it as easy as possible for yourself. So, basic conclusions. Modern monitoring technology is impressive, but it's effectively useless without a human at the wheel. Your car doesn't drive without you pressing the pedal. I recommend try not to get bogged down in purely having the most modern and the most complex systems if you don't have the adequate experience in processes to analyze it. It might just be overwhelming. They do, however, hold a lot of potential. If you're able to fully extract all the value out of your system, then go for it. It's fantastic. We need more champions in the industry of experience with monitoring and push for better and higher quality monitoring programs. At the end of the day, the goal is to prevent harm to people and the environment. Monitoring is an important tool in the arsenal for this, and it has and will continue to save lives as we go on. So it's obviously very important. So thanks for listening.
All right, thank you everyone. This is the hardest shift. You've all just had one beer and a little bit of food, so I'll do my best to keep us all awake. So my name's Lockie. A lot of you I'm yet to meet, a lot of you I've known for a long time. Just a little bit about my background. I worked for a company called Ground Probe, who makes slope stability radars. Had 12 wonderful years with Ground Probe, and now I work for a small company called Geobotica, who is very close with Ground Probe and friends with them. So look, I'm just going to start by just telling you a story. So I'm here to tell you about a new instrument, not a really big monitoring platform, but we're going to shrink it down to one little tiny thing that this startup in Brisbane has invented about 5 kilometres from where we are here. So I got a call soon after I started Geobotica from Leslie Munsami, who looks after Anglo American's global geotech team. And he came and he saw me and he said, look, I've inherited this role and I've inherited the platinum mining, underground mining operations. and we're getting all of these fall of ground in the narrow stopes, and we need to do monitoring for that. And I said, oh, it's great, yeah, let's have a chat about that. And then he says, have you ever been in an underground platinum stope? And I was like, no. And he said, well, it looks like this, but it's just nowhere near as clean as that, and of course there's no light. I was like, oh, okay, that's a little intimidating. He says, yeah, but the way you get to work every day is you jump on one of these.
It's like T-bike.
Yeah. Which is, you know, I've actually ridden on it, and once you get over the fear factor of going about 2 kilometres underground on a chairlift, it's actually a lot of fun. And the other thing is they have speakers that play like really upbeat African music on the way down the mine, which is really fun. But anyway, that's how you get underground. I was like, okay, this is sounding a bit hard. Then when you get off that, you then have to walk, you know, 1-2 kilometres to your work area. And then you crawl in. If you're having a good stope, you're at about 1.2 metres high to 1.5 metres high. And he says, this is real mining, Lachlan. And I was like, oh, okay. When I went there, I also had the pleasure of, the guys love it when a visitor comes because they're like, sweet, someone else can do my job for 20 minutes. And they bring you in and you have to sit on this air leg and give it a try yourself, which is pretty intimidating. And you can imagine getting ground support in there is difficult. And so the most common form of ground support are the props at the front, you can see against the face. And then you have the wood packs, which are over here behind you. And then further behind that is a pillar, which is often concrete, often with wood packs behind that again. So I was like, okay, well, that's, you know, we've just started this business, I got no money, so keep talking to me. And he says, I need you to build a slope stability radar for there. I was like, that bit's all right, I can do that. And he says, yes, but you can't have any moving parts. And I was like, oh, okay. So, well, how about a laser scanner? He says, no. People are going to like drag this crawling through all the way to the face. I was like, okay, well, that's not going to work. He says it's got to fit in your pocket. It's got to be smaller than a self-rescuer. I was like, oh, have you seen how big they are, Leslie? They're like, you know, you need about 2 ton to drive these things around. And then he says, also, it's got to run on batteries for at least a week, longer if you can. I was like, well, we do about 8 hours at the moment on surface before the engine kicks in. And then he says, it's got to be waterproof, dustproof, drop-proof, all the proofs. I was like, oh, this is, you know, this is hard. And then, but you also got to filter out the people and the machinery and just look at the rock. He says, for some reason, and the last bit is, it's going to only cost $20,000. He says, I've talked to everyone and no one wants to do this. I was like, oh, I wonder why. But he says, I'm guessing that you do because you've just started a business and you need my support. And I was like, oh, I am the man for you. And so we jumped in and said, okay, we're going to make a nano radar. We're going to call it. So the first thing to do was to get over to South Africa, but it was during the travel bans in COVID and we couldn't go there. So we thought, okay, well, what are we going to do next? So we sent a laser scanner underground and we scanned a stope and we got that back and we took the measurements, and I was lamenting at a barbecue over a few too many beers with a chap, and it turned out that he is the set designer for Mad Max. He's also the guy who built the Brisbane sign here, and he just does random weird projects. And I told him about this. I said, can we build an artificial stope here in Brisbane? So that's what we did. So first thing he did is he went over in the dead of night to Kangaroo Point and poured silicon over the rocks and peeled off the fast-setting silicon to make a mould of rocks. And you can see we then cast them with expandable foam. And then we had to stitch all of those little bits of moulded rock in with another surface. And we made this 1-to-1 scale stope that you can see on the left-hand side. And that lever up there, you pump it, and every time you pump it, it induces 0.5 millimetre of deformation on the roof of this artificial mine. That's it on the right-hand side, what it kind of looks like on the inside. That's me inside Brisbane's first ever platinum stope. And we would have, every 2 weeks, we'd all have to pull on our PPE and go in for the Teams meeting with Anglo American, and we would go and talk about the progress and the design and how we're going to interact with this thing to make it work underground. So that's a screenshot of me looking very interested in the back there. But yeah, it was a terrific way to do those regular meetings. And then this is after quite a long time actually. It's about 2 years of R&D. This is the final outcome of what we built. So This is nano radar, all of those things that we wanted to talk about. The thing you can see there is a folding tripod, and I will get to tailings, you just got to believe me on that. But what you do is, as you walk around, it knows that you're moving when you're underground. You flick open the tripod a bit like a flick knife, I guess, and put it down. It then will detect that it's stable and it'll start a new data set. In this top corner there is a 90 decibel siren that we had to pick the frequency of the human voice, the frequency of machines, and pick one in between so it will penetrate through. Also, the reason it's this odd colour is that when an alarm triggers in the zone, the whole thing illuminates like a lantern. And yeah, it measures sub-millimetre displacement, just like a traditional slope stability radar, but it has a whole bunch of antennas under this strange little dome here, and it takes like a radar photograph, and it does that every 2 minutes and can measure side to side. So that electronically steers the beam. It scans every 2 minutes, it goes out to 80 metres range, measures sub-millimetre change. You can see the scan area is about 120 degrees, so we could scan this whole room. Inside it is a Wi-Fi connection as well, and that can then connect where you can view the data remotely. The little screen on the side is the same technology as a Kindle, so it's very low power. So we set the screen and then we turn off the power, and that way the batteries in this can run 24/7 for 9 days when you're underground, which is long enough to meet one of his difficult specs. And then the next thing, inevitably, that the question was, well, can we use it open cut in pits? And well, the answer is yes, we can. This is our software, and I'll take you through that in a minute. And then, well, what about tailings embankments? And the answer for that one is yes as well. So let's just talk about this. This is, we've very kindly been given permission by this customer to talk about this case study under the condition of anonymity. So let's just enjoy it. All I can say is that it is a Queensland facility. Okay, so let's have a look at it. So what is the issue? The issue here is this is our software, a photogrammetry model of the embankment, the two walls that we had to monitor, and inevitably tailings are so often right up against the boundary of the mine, so of your lease area. So putting a traditional radar, we just couldn't get one far enough back to monitor the whole area. So we needed to deploy many radars, traditional or otherwise, all the way along it. And of course the cost of deploying, say, 10 traditional radars is probably a lot more than needed. The flip of it was, could we maybe put in some GNSS sensors, was an alternative option, but really when you have a system that's come from underground at this low cost, it could be really attractive to put quite a lot of them. So next we've developed this little box. It's just, you just pick it up and drop it off, and then it starts monitoring. It connects to a Wi-Fi network. There was no phone signal out there, so we've set up a Starlink, the SpaceX Elon Musk connection, and we have 13 radars along this facility. So it's covering about 1.5 kilometres with real-time data. So the next thing is, what's the TARP for monitoring this particular case study? So we have two triggers. The first trigger is 25 millimetres a day, and the second trigger is a total displacement of 250 millimetres since monitoring began. So if we just recall, a GNSS, the alternative, we're talking about, depending on the manufacturer, maybe 10, 20 millimetres of noise that you're going to get between readings, which is why maybe radar is a good option in this case. So let's check out the data for this facility. So we're just highlighting the 13 of these. We'll just deep dive into one of them. So we've set the chart there to show what the velocity TARP is. If I showed it at 250 millimetres of cumulative deformation, you wouldn't be able to see it. It would just be a very flat line. So you can see that's 4 months of monitoring data there, and sub-millimetre precision in real time, so you can action that. If we just check that out, this is the movement at the toe. If we zoom in a little bit more on that one, if I expand that chart out a little bit more, you can see kind of the level of precision over that period of time. And there is a seasonal, not only just a diurnal change that we have to manage, there's a seasonal change that you can start to see that comes through the data as well. But again, very small sub-millimetre changes. So this is the largest amount of settlement in that area. It had just recently been dozed, and there's been little pockets of settlement on the surface itself as the material sort of self-compacts, which has been interesting to see. But essentially, stability there was established. At least deformation stability at the moment is certainly been established. But look, the question was that there's on the bunker of this CDA there was an area that needed monitoring. So we'll jump over and check that out. Now this is not in colour, just also to help anonymity here.
Just giving it away. But we won't tell it.
Okay. Yes. Fair enough. Okay. So if we just zoom in here to our software and have a look, so you can see if I click areas here where they're stable, you can see very little deformation. I could just move this slider to change the heat map, and you can see there that's currently set on 19 millimeters over a 2-month period. If we bring that up, you can see at periods of rain, you see this rapid acceleration. You know, about 2 millimeters here, a very small area there that let go, and then a regressive movement as it slowed down with continued deformation. You know, as there was no rain, another rain event here had a few other little areas the very small areas that released, and then another regressive area before we get progressive again. And as we click around, we can just add more points to that and see, you know, there are some here where they did not have the same time of the acceleration and deceleration periods throughout the slope. You could just come and grab an area to look at all of those, or just look at an average of those displacements in that one zone if you wanted to. And then, you know, that's the colour palette at the top also matches. Or back, yeah, also matches. If you want to view it the other way, some vendors like to show it upside down. We just show it both ways. You can flick between negative deformation or positive deformation, however you want to visualize it yourself, whatever you're used to really with other different sensors. So yeah, that's sort of some of the features of the system. Now what we can do is zoom out, and I believe we're just going to, what are we going to do now? We're going to move it around, click some other points. I'm supposed to be talking about something else. There's also another feature in there that's called layers, which really helps with reporting, where you can group different points together and just quickly report on those rather than on individual areas. So yeah, if we just say, look, let's zoom in right to the start of that period as well, and let's try and see what the displacement precision is between scans. So you can, sorry, the cable I think has got a little connection. You can see the very low level of noise. So that's you know, much less than 1 millimeter between scans. So this is the layers feature where you could group areas together. Clearly this one's pretty obvious what you want to look at, but here we want to group all of the points on the floor and separate those from an area that might be on the failure, for example, or in other zones. So yeah, that's a little bit of a quick tour of the data. You might say, well, that's pretty easy to measure 20 millimeters of deformation. So let's jump right into the first few hours and see straight away, within hours, that first displacement was visible over a few millimeters. And then if we just expand that out to being a few hours more and put that on a 5 millimeter plot, you can see very clearly that within 12 hours of deploying this system, it was very clear that that was the area that was deforming. Which is pretty cool. And if we compare that with adjacent points at that same period of time, you know, sub-millimeter there, just below it on the slope, whereas the area that's moving is still moving by several millimeters. And those same points that I selected, if we go for the full 2-month period, you can see they've remained stable the whole time as opposed to the collapse itself, which is great. Now, we're just going to end with something a little bit more fun. So, I love working with Brazilian people. They're just terrific people. I'm sure you've all felt the same thing. There's a different energy about them. And if I thought the South Africans gave me a hard challenge about underground, then I just hadn't spoken to enough Brazilians. Because they said, we've got a problem that we have, I'll just call it linear infrastructure, where we have a lot of slopes that we need to manage. And the problem is the local people don't like us very much. And every time we put a sensor out there, they go and smash it up. So what we would like to do, if you're into audacious, ridiculous goals, is can you make a radar look like this rock? Well, it's, you know, it's kind of small enough, but so what we did is we went and we got a sheet of plastic that Lego's made out of, that same plastic. We heated it up to 170 degrees and got a rock that we thought was about the right size, and then sucked all of the air out of that, and we used that to make a mould. And then you can see this is the solid mould that's still pretty hot that to then pull off and use. And we found this material that these guys in Ireland make. Now this is an acrylic, so it's plastic, and they use it generally for jewellery and sculptures, but it's got little bits of rock particulate in it, and you can pour it into that mould and then it will set and look like a rock. And the challenge for you guys is to tell me which rock is real and which one is a Wi-Fi repeater. So the one on the bottom is actually the fake one, and the one on the top is a rock. So we have Wi-Fi repeaters that look like fake rocks, and we also have radars. Now that little antenna dome has to poke out of the front. So, you know, if you see like a half a ping pong ball in a rock next time you're in Brazil, you'll know you can get a free radar. Yeah. So that's been a really fun thing to do. So look, we're just a very small, we are definitely the smallest company in this room here today. And, you know, as a startup that's based here in Australia, in Brisbane, we're trying to make a difference to this industry. So if there is any way, if this has any interest to you, you know, I'm usually the last person to do the pitch, but as a small business rep, I need to kind of ask if you do have any interest, if you want to just try one out, let me know. We'd love to send one up to a tailings dam here in Queensland. Thank you very much, everyone.
Okay, thank you. First of all, oh God, excuse me too. That's going to be a very hard task to follow on from Lockie. That was, mate, really interesting technology and yeah, awesome work. So yeah, unfortunately, my preso is going to be a bit more droll and a little bit more technical, and I don't have the what's the word? Pizzazz. Yeah, I don't have the pizzazz of Lockie, so. But anyway, we'll get there.
You've got Zaza
What's that?
You've got Zaza he's got pizzazz.
Yeah. First of all, just a little bit about me. I also worked at GrandPro with some of the other people here. I've worked there for about 15 years before I went over to IDS, and I've been with IDS now for 4 or 5 years. So I've been in this the radar monitoring sort of arena pretty much for almost 20 years now. So yeah, I've spent a lot of years travelling around the place, installing, deploying, fixing, analysing, all that kind of stuff. So, okay, so I wasn't really too sure what to put together for this, but that's what we're going to talk about over the next 20 minutes or half an hour or so. So some best practices. I've included there, well, I'm not just going to talk about like normal radars, I'm going to concentrate on what we call SM and SMV and SMA, which stands for slow movement analysis. So I'm going to explain how we go from normal sort of interferometric radar processing, okay, to what we call slow movement analysis. That has benefits for tailings dams, okay, because we may not necessarily want to see what's happening in real time. We may want to see really, really slow trending displacements that occur sometimes over years. Okay, so that's what we'll talk about in a little bit of detail later. We'll have a look at a few case studies, but specifically I want to talk about data correlation and how we can correlate radar data with with PRISM data and INSAR data and GNSS data and all that sort of stuff. So we'll just, not in any detail, but just have a look at a few examples. And then right at the end, I'll just very quickly talk about how we have agreements with other third-party companies, Rock Science, for example. So we have the ability there to use the data from both software packages to check if your modelling's right, things like that. Okay, so that's just basically what we'll talk about. I'll try not to bog down too much. I'll put a couple of slides here at the start that I'm not going to go through in any detail because all you guys are TSF professionals, but just as just some basic points. Dynamic, active structures, okay. I think everyone's spoken about this so far. In my opinion, if you want to actively monitor a tailings dam, okay, you want to try and use as many different technologies as you can. Okay. There's lots of technologies out there that produce really good data, countless technologies out there that can be used for monitoring tailings dam, but when you have one or more, or 3 or 4 or whatever of these technologies all together on the one platform, it gives the data more you can trust it more. Okay, if you're seeing the same data from 2 or 3 different instruments, then chances are it's correct. Okay, and one of the big things too with tailings, with TSF structures, they're often vegetated. Vegetation brings in big problems for any synthetic aperture radar technology. Okay, any kind of interferometric radar, as a basic assumption, needs a coherent signal, a coherent surface. Okay, it's not going to work without a coherent surface. And obviously, if it's vegetated, we need to look at other techniques to try and remove that interference. Yeah, and I'm not, you guys know, I'm not going to worry about any of that stuff there. Okay, fundamental risks. Once again, we're all, you guys all are all over this, know more about it than me. All the different kinds of risks there, failure types. Not only that, but a tailings dam is different to like a normal open cut wall, for example, because it's full of material. Yeah, and the material that's in the tailings dam, water content, compressibility, strength profiles, etc. Okay, all add to the monitoring challenges that we're going to get. I've got this data here from that Chambers 2017. You can have a look at that later if you want when you go through the slides, but there's probably more up-to-date information than that available now, but that's just something I'll put there. Okay, we've got INSAR people. We've got INSAR people in the room. We've got Geobotica people in the room. We've got all kinds of people in the room that sell and promote their own monitoring technologies and strategies, which is cool. Okay. Connected ecosystem of monitoring sensors, in my humble opinion, is, especially when you get to more bigger, complex TSF structures and things like that, that's what we all need to be aiming for, okay, to get a complete picture of what's going on with our facility, TSF facility. Okay, so we've got our normal ground-based SAR, like GB-SAR over there on the left, radar data, tail stations, obviously INSAR, there's VWPs, there's tilts, there's all kinds of different instruments, okay? Bringing everything together on the one platform. And once again, we've seen various examples here today already of different products around the place. Okay, there's lots of them. Ours is called Hexagon Geomonitoring Hub, but it's very similar to Navstar and it's very similar to many of these products. It's there to try and bring all these data sets into the one software package so you can visualize everything at once. All right. So yeah, connected ecosystem of monitoring sensors. Let's get everything together on the one platform for the best monitoring. Okay, but it's not just as simple as that. What technology you go for and how many technologies you go for is dependent on the risk assessment and or the risk profile or the risk aversion of the company or the organisation or the body that you happen to work for. Okay, so we can go from like very low risk down one end. So it might be an old TSF, for example, it's dry, it doesn't rain much. There's not much exposure in relation, if it failed, there's no real exposure to people or anything like that. In that sort of situation, you can just review it as required. Okay. And of course, we go from the very low risk all the way through medium risk and up to critical risk at this end. And this is what I was sort of mentioning before, where we want as many sensors as possible on the one platform. Okay, yes, so critical risk, and we can see there. So we've got, like, there's a big exposure there. People could get hurt or injured. We could get a slope failure, okay, that kind of thing. We really want real-time monitoring. multiple technologies and the ability to set alarms and things like that. Okay, so that's the, as geotech professionals, and when you're thinking about what kind of monitoring technologies to implement, obviously that's what we need to look at. Okay, so I'm going to try and not make it salesy because I don't really do salesy stuff, or I like the technical sort of stuff. But IDS, we have our software here called Guardian. Some of you have probably seen it, some of you maybe haven't. But I'm not going to talk about Guardian specifically. I'm going to specifically talk about the SM and the SMV algorithms. Okay, so slow movement and slow movement vegetated. Okay, so they're specifically for detecting extremely slow movements. Okay, not millimetres per day or anything like that, like millimetres per month. Okay, so really, really slow, deep-seated, long-term linear trend displacements that is what you may need to understand. You may need to, a lot of people fail to understand that they really should be running a slow movement campaign as a first up sort of monitoring strategy. You can see what's moving there that you may not already have known about. Okay, and when you see that, you can then concentrate your monitoring on those particular areas. Okay, it also runs. It's just software, so well, it's a different algorithm, but Guardian slow movement, it actually runs in concurrently with real-time Guardian processing. So you can have the radar scanning away, collecting real-time data. Okay, so you can still alarm and do all that sort of stuff for your real-time movements that you would normally. But you can also run a slow movement project on the side as well. Okay, and I'll explain how it all works. Okay, so why use GBSAR, by the way, ground-based synthetic aperture radar. INSAR is also a synthetic aperture radar, but ours is obviously on the ground. They use very similar interferometric technology. They measure phase change, and from that phase change they infer displacement. Okay. Yep. And we'll see there. That's a data set. So that's actually a vegetated TSF slope. It's 10 months worth of data. Okay, and we can see the results over here. So it's nice, clean data. When things start to move, there's nice linear trending. We can see that this is just a plot, so something else has happened here, and it's the displacement trend has changed. But we're able to record really, really low rates of deformation. So this particular data set here is approximately 0.6 of a millimetre per month. Okay, and it's not post-processed data, it's not just something that we make up, it's actually real data. I'll show you how it works in a minute. There's other technologies around that can measure really slow rates of displacement, INSAR being one of them, but I don't know if INSAR can get down to a similar rate with as clean a data. Probably not. I don't know.
Definitely not.
Yep. Okay, so that's why so why do we use radar data and these particular algorithms for slow moving TSF? That's why. Okay, that's the kind of displacement rates we can detect. Okay, so let me stand around here. So this is how it works. Once again, very basically, I'm not going to go into the details of it because we just don't have the time. But in the standard processing up the top there, if you have a look at each one of those like cards or slides, that's just a representation of each interferogram as it comes in. Okay. What we do with slow movement and SMV it's essentially a subsampling process that we use. So instead of looking at every scan that, depending on the system, can be anywhere from every 40 seconds out to every couple of minutes, okay, we set a subsampling time period. In this case it's 24 hours, and we just sample one interferogram every 24 hours. It can be 12 hours, it can be 6 hours, it can be 3 days, it's whatever you set up in the software when you're setting up a project. The amount, you should, I can't give you an answer as to what is the best subsampling time period to use, because it depends on the magnitude of displacement that you're hoping to detect. Okay, so you've got to have a little bit of background knowledge about what you think may be happening on that slope. Once again, I'm not going to go into it because you don't have the time, but our processing uses adaptive thresholds, and we also use a PSI, stands for persistent scatter interferometry, similar to INSAR once again. So we actually use PSI interferometry, and we use statistical analysis to classify our moving and non-moving pixels. Okay, and it's all based on correlation in space and time. So if there's an area of a high wall, for example, that's moving, the algorithm assumes that, well, if it's real movement, if it's moving now, it's going to be moving in an hour's time, it's going to be moving tomorrow, and it's going to be moving the next week. Okay, so that's in time, that's correlation in time, and correlation in space refers to, obviously, if there's an area of the high wall that's moving, that area is going to be moved, the same area is going to be moving as time progresses. So it's not going to all of a sudden be moving over here, and then it's going to be over here and down here. Okay, because if it is doing that, it's most likely due to some kind of atmospheric disturbance. Right. So having all that in the back of your mind, what we're essentially doing with this slow moving or subsampling process is we're reducing the slowest detectable movement that the radar is able to detect. Okay, so if we get a scan every 1.5 minutes, okay, then we're roughly going to be able to detect 0.67 of a mil per day. And if we subsample once every 24 hours, okay, that's dropping off. Now, this is not just a standard calculation because it takes into account multi-scaling as well. So it's not just a multiply deformation. So it's not just multiply a particular amount of deformation by a particular amount of scans per hour, for example, to come up with that. There's also multi-scaling that's happening as well. But to cut a long story short, that's what we're doing. We're minimising that slowest detectable movement, or minimum measurable velocity. In radar world, everyone talks about phase ambiguity and maximum measurable velocity. That's important as well, but this is the opposite. Okay, so we're changing that minimum MMV there. So what it's doing, essentially over time, all these phase residuals that we get, they just add up and they add up and they add up and they accumulate these little 0.1 of mil or even less movements. So they're phase residuals from atmospherics and other things, and that all adds up over time to basically swamp out some of this slow movement. Because that's pretty much what we're doing. It's very simple there. All right. All good? I just want to talk very basically too about the vegetated algorithm. I mentioned before, well, about coherence. Okay, all radars, all interferometric radars need a coherent surface to get good, reliable data. Without a coherent surface, they will not work. You'll just get noise, essentially. And now, remember here we're talking about a vegetated slope. So over on the left there, okay, you'll see the coherence coefficient and the effects of vegetation on the coherence coefficient on the left. Okay, so what we're aiming for in radar land is to have coherence up near 1. Okay, if we've got a coherence of 1, that means that that particular point is exactly the same as what it was the previous scan. So it's a coherence of 1. It's a dimensionless value, coherence, that's calculated by looking at the phase and the amplitude information for each of those pixels. Okay, and as you can see quite clearly, vegetation stuffs it up, right? Think of this here as like a resolution cell of, so one radar resolution cell. In the case of one of our radars, that is going to, at a kilometre away, it's going to be approximately a little bit less than, a little bit over 3 metres squared. Okay, radar doesn't just pick up one measurement from within that cell. It does a very complex vector addition and adds up all the different little bits of backscattered radiation that it's getting from that pixel. Okay, and in the case of a vegetated slope, it's equal to the sum of the backscattered radiation from the ground plus the sum of the backscattered radiation from the vegetation. So it all goes into one. Okay, and up above there you'll see what I mean. So there's some energy reflecting off the ground, there's some reflecting off the vegetation. Okay, and that's essentially very basically what it looks like there. I'm not going to go into it, but it uses it looks at the decorrelation time, okay, in relation to the actual interval, the scan interval, and it comes up with a velocity. And then it compares that to the uniform velocity on the radar line of sight that it gets from the ground. So it compares the two velocities, and it averages them out. Okay, and all being well, it makes its best attempt at removing the effects of the vegetation. It's not perfect. It's a work in progress, but we get pretty good results with it. All right. Just a couple of pictures as an example. That's one of our synthetic aperture radars in Samarco, monitoring that tailings dam you see in the background. It's called a synthetic aperture radar because it doesn't actually have a, it synthesises a dish essentially by the length of that linear scanner there. So the length of the scanner synthesises the size of a parabolic dish, pretty much, very basically. Okay. So that's just an example. Here's another one. Once again, a radar up there on the right. It's monitoring that tailings facility there. It's vegetated. Okay, so that is vegetated, and we can see in the data that if you know radar data, that's actually relatively clean data for a vegetated slope. Same again there, just another picture. Yeah. Case study time. Yep, data correlation. So I just want to talk about how we can use data from different instruments and how it makes the data a lot more valuable when we can correlate the two data sets. And if they show the same thing, then it's a good thing. So this particular tailings dam here, I can't actually pronounce it properly, so forgive me. Corta Atalaya. If anyone can speak Portuguese or Spanish, feel free. But and we'll see that in this particular tailings dam here, they've got 150 prisms, 4 GNSS stations, they've got 1 GBSAR radar, they've got piezos, open piezos, standpipe piezos, inclinometers, etc. So they've got all these different instrument types there. Okay, and the beauty of being able to bring all this data into the one platform, like Geomonitoring Hub, for example, or Navstar, or whatever your product is, we can see the ability to actually compare the data from different instruments is really, really powerful. So we can see there that the prisms on the TSF wall are basically showing essentially exactly the same amount of movement as the GNSS station as well. So it gives us confidence in the data. Same thing with radar data. If you don't understand what you're looking at here, that's just that's an example of some radar data with displacement on the left over here and amplitude on the right. We can see there that we've also pulled the prisms. So we've pulled these 2 prisms here into Guardian. Okay, and to make the data comparable, we've had to we project the prism information on the radar line of sight. Okay, because prism, as you know, it's not just measuring displacement. We've got vertical and horizontal components, things like that. So if we pull the prisms into Guardian, stick them in the right X, Y, Z, and project them on the horizontal line of sight towards the radar, we can make the prism data comparable to radar data. Okay, and we can see there as well high correlation between what we're seeing with the radar, okay, which is the purple lines, and what we're seeing with the prism data as well. So we're able to bring different data sets into the one platform, correlate what they're saying, and straight away you've got almost 100% confidence that is, you know, that's a highly accurate data, or it's essentially doing what it's telling you it's doing. Oh, that just, sorry, I didn't go through the animation, but yeah. So. Yeah, so just as a bit of a summary, pretty much you can read that, but yeah, the data's been confirmed with GBSAR radar data and also prism data. Okay, also we can also see there's a little discontinuity appearing at the top there in that blue area as well. Yeah. Okay, so comparable data. It's a really good thing. We've got myself and Christian up the back, we did some really cool stuff at a mine in Queensland. We ran like a subsampling project that went over like about 2 years worth of data, okay? And we actually identified a movement on the north wall of this mine site that they did not even know it was happening. Okay, and they would not have known it was happening when they were looking at real-time data because it's too slow. It just gets swamped out by all the system noise and all the phase residuals and things like that. Not only that, but we could also align it almost exactly with what their prisms were displaying as well. So it was really powerful data. Only possible with subsampling. Just another case study. It's pretty much the same. So we're just comparing prisms and some radar data. Okay, and we can see here once again radar data on the left. We've pulled in some prisms, put them in the right location on the DTM. We've interpolated it, so we've projected the prism data on the radar line of sight to make it meaningful or comparable. Okay, and once again we're able to see almost exactly the same behaviour with prisms and radar data. Okay, so that's yeah, really cool stuff. Any questions? No? 2 more slides. I'll put you out of your misery shortly. Okay, mapping and modelling and spatial validation and things like that. So we have partnerships with other third-party companies, in this particular case Rock Science, and we are able to use with some really good results all the different software packages that Rock Science has. So on the left there, that's their 3D limit equilibrium software called Slide 3D. They've put in their failure surfaces there, and they're able to basically work out factor of safety wise what could potentially happen there in that wedge. Okay, that's occurring. Finite element analysis, the next one, RS3. Okay, so they're able to model the displacement in a particular area by, like any finite analysis, by entering parameters and seeing what the results are. But what's really good with radar data is you can then, especially with Rock Science, we can import different data sets both ways, from one software package to the other or the other way. So we're able to import our radar data into the Rock Science product and basically see exactly what's happening, and essentially we're able to verify their modelling. Okay, so does their model, so the inputs and the strengths and the strains and everything else they're putting in their FEA software, does that align with reality? Okay, and in this particular case here, yes it does. So it's very powerful when you get down to some really deep level, really cool analysis by using data across these different software packages. Some of you guys probably do that already, no doubt. Yeah, I won't speak too much about this. And it's just another example there. Okay, once again, 3D finite element analysis. Then they've back analysed it, okay, to understand what kind of displacements are happening there along those strains and the faults and things. And then they're able to use the radar data to actually verify it and correlate between the different software. Okay, so yeah, that's about it. So yeah, just to summarise, the type of monitoring you're going to introduce in a TSF facility is going to depend on your risk analysis or your risk aversion or whatever. Obviously, from low risk up to high risk will change what kind of instruments you're going to use. Radar data being one of those things. And what's really cool with radar data is, well, with the IDS data, you can do that subsampling and detect extremely slow, low-level displacement rates that you probably cannot detect with any other monitoring technology that I'm aware of. Then, having said that, if you pull all the different technologies that you've got into the one platform, you can also use that platform to verify that your data is correct. Okay, compare data from different data sets and get a really good understanding of what's happening pretty much. So yeah. Cheers.